Okay, we are almost there. Just give me 1 second for the stream to show up here. All right, we are live. Okay, back to this. Hi everyone, and once again, thank you for joining today. Yet another wonderful talk in our speaker series that we do every month. Ever since the pandemic started, we have been doing this on Zoom and streaming them live to YouTube, so people can watch it there, as well as it gets recorded, and people who can't make it can go watch it later. And a little bit of SJAA, like if you are unfamiliar with the group, we are an amateur astronomy club here in San Jose. And we have been around for a few decades now, and it's a very active club, and with a sufficiently large member base, and it's a lot of volunteers who are trying to do the outreach, science outreach, which is the main goal, I think, and just share the hobby together. I think that's the other important thing. But with that said, we are always looking for more help. So if any of you would like to help out, please feel free to reach out. You can find out more information by going to sja.net or finding us on Meetup with SJ-Astronomy. Either way, it works. Now, before we get into the talk, just a couple of logistics things. Please mute yourselves if you're not today's speaker, of course, and so that we don't have any echo coming in from anybody. That really causes issues sometimes. I will have a way, like a superpower to mute anybody if necessary. Just please don't get offended if I do that, if it's disruptive in any way. And then the other thing is, we were just discussing before you all joined, Dr. Basri would like to take questions as he goes. So for that, you may unmute yourself and ask your questions, or if you want to just put them in chat, I can relay the questions to him, and then you will have the answers, and then I can similarly watch the YouTube chat channel and like get questions from there as well. So with that, now let's start talking about today's topic and our esteemed speaker. He's not new to Bay Area. He did his BSc at Stanford and then went away for a little bit, but then came back to Bay Area and has been at UC Berkeley since then. And he's today going to talk to us about red dwarfs, which is always a cool thing, but it's even an interesting topic when so many of exoplanets that they're finding now are red dwarfs, and then are they really livable, and what is the potential involved in that? He tells me he's retired, but he's currently still very active with research, which is very interesting to me. And I guess we are all very curious to find out more about his research with red dwarfs. So without further ado, Dr. Basri, please take it away. Thank you very much.
Well, thank you very much for inviting me to speak with you this evening. As was said earlier, especially with a smaller group, it's nice to kind of get into a conversation rather than me just talking at you. So if you have any questions along the way, feel free to either interrupt me or put them in the chat, and I'll get them. And I think that'll work well. So let me share a screen. And start the show. So we're good, Sukata? This is seeing the slide?
Yes, that looks great. Thank you.
Okay, great. Okay, so today's topic is, are red dwarf planets habitable? And as Sukata already pointed out, most of the announcements in the last 5 or 6 years, actually 10 years, of exoplanets, which are both near Earth in size and also in what's called the habitable zone, which are the most interesting planets in terms of potential life, have been found around red dwarf stars. And there's reasons for that, and I will tell you what they are. But the question of whether such planets are even habitable is kind of one of the biggest, hottest questions in exoplanet and astrobiology research right now. So that's really the main topic of my talk. I assume you are all kind of familiar with red dwarfs, so I won't say too much about them, except red dwarfs are the most common kind of star. That the average star is a red dwarf. About 3/4 of all the stars that are made are red dwarfs. And by red dwarf, we mean stars that are sort of half a solar mass or less, and they get down to a little under 1/10 of a solar mass. They have about half the surface temperature of the sun or less. But the main thing about them is they are very much less bright than the sun, very much less luminous. Somewhere between 1% as bright as the sun, all the way down to 1/10,000th as bright as the sun. And so the little moving GIF over there shows the solar neighborhood. The sun's at the center here, and all the stars within about 10 parsecs. And you can see most of them are red dwarfs. And as amateur astronomers, you may realize that you've never seen one. Even the very closest star to the sun is a red dwarf, and it is not visible to the naked eye. So they are really quite faint. The other thing we've learned about red dwarfs in the last decade or so is that they tend to host smaller planets. They're smaller stars and they host smaller planets. And by smaller planets, we mean Earth-sized planets. So there's another reason as well, but basically all the habitable Earth-sized planets, excuse me, are around red dwarfs. So I'm sure you're also familiar, wow, scratchy throat, with how we find exoplanets. There are two basic methods. This was the first one, which is the radial velocity method. So here we are just looking at a star, and we're measuring its velocity, its radial velocity, that is the velocity towards and away from us, using spectroscopy. And I'm sure you know that this is actually rather difficult. The Doppler shift due to a planet is sort of a part in 100 million of the wavelength of the light you're trying to measure. So that was why it took us so long to get this method to work. But in principle, it works fine. It actually doesn't work yet for Earth-sized planets. They don't produce enough of a radial velocity shift. So the planets that are found this way tend to be quite a bit more than one Earth mass. The good thing about this method is if you can detect a planet, you can also get an idea what its mass is. It actually only gives you the lower limit to the mass because you're not sure what the orbital inclination is. But at least we can say, well, it's near Earth mass, or it's already, its lower limit is Saturn mass or whatever. And in order to understand what kind of planet we're looking at, we'd like to know both its mass and its size. So luckily, the other method for finding planets does give us the size. So this is the transit method. This is something I was involved with. I was one of the co-investigators on the Kepler mission, and there the idea was we wanted to see transits of exoplanets. Let's see if this actually works. Yeah. So. And I'm sure you're familiar with this as well, but the idea is if we're looking at a star and a planet happens to cross in front of it, it causes the light from the star to be blocked a little bit while the planet's in front, and then we'll clear again. So of course we don't see the actual star and the planet. All we measure is just this brightness curve, but it has a characteristic shape and time, and if it's really a planet, this transit will occur periodically with the orbital period of the planet. So if Jupiter crossed in front of the sun, it's about 1% the area of the sun. It's about 1/10 the radius, so 1% the area. So you'd get a 1% dip in the light from the sun. But here's an actual picture of Venus crossing the sun. So that's very much an Earth-sized planet crossing a solar-sized star. And there, the amount of area for the planet compared to the star is only 1 part in 10,000. So that's much harder to measure. And in fact, we basically need to go to space to do that. And that was why the Kepler mission was flown. You also need to, you have no idea when this is going to happen. And if it was an Earth around the sun, it would happen for a few hours once every 365 days, right? That's the orbital period. So you need to be looking all the time. You can't, and that's why ground-based transit experiments are much less efficient, because half the time they can't look because it's daytime and then there's clouds and stuff. So this is really a space-based project, and the Kepler mission really totally showed that. So this is, one display of sort of what Kepler found. The radial velocity method had been finding planets that were in this part of the diagram here, and Kepler really opened up the whole field. Although, as you can see, it's still orbital periods that are kind of 100 days or a few hundred days at best. Most of the planets that we found had short orbital periods because it's easier to find them, right? They come around more often, and so you can dig them up out of the noise. So here's a Jupiter radius here, Neptune radius here, Earth's radius here, and yeah, we found lots of small planets. In fact, what we found was nature likes to make planets that are small. The radial velocity method kind of gave people the impression that Jupiters were the common kind of planet, but that was because those were the easiest to find with that, and it couldn't find these. So Kepler showed that actually in nature, most planets are smaller than Neptune, and many are the size of the Earth. Kepler had trouble down here, so this is a very incomplete census of Earth-sized planets. So basically, we know that Earths are very common, and also these planets in between the size of Neptune and Earth are very common. This might be the most common kind of planet. We don't have any planets like that in our own solar system, but they exist quite a bit around other stars. And so one question is, what's the nature of these planets? Are they super Earths or are they mini Neptunes? And the answer is almost certainly the ones that are bigger are mini Neptunes, and the ones that are smaller are super Earths. And I'll talk a little bit about where the dividing line is later in the talk. Let me stop at this point and just see if there are any questions. This is probably familiar material. No, okay, good. We'll go on.
Let me check the YouTube channel once too before we proceed. I think that's clear as well.
So, Dr. Basri, I just
there you go.
In the slide about introducing the sensitivity 1/10,000 like that.
Yeah.
I just wonder how space telescope can assign the region of interest to point out only that stars, because I think that field of view would be very small. How it can detect the kind of very accurate sensitivity.
Yeah, so you have no idea where to look, and so the Kepler project just picked a place in the sky where we would have a lot of stars in the field of view. So it was a Schmidt telescope, so it had a field of view of about 100 square degrees, so much better than a normal telescope. Mm-hmm. And we just picked it. We picked a location in the sky near the Milky Way, but not in the Milky Way. So the Milky Way has too many red giants and too many stars, basically. So we looked a little bit off the Milky Way. We had to not look anywhere near the sun, so we looked away from the ecliptic. And I have a slide, but I didn't have it in this show. You can sort of pick a region either in the northern hemisphere or the southern hemisphere that satisfies those basic criteria. And since we were northern hemisphere astronomers, we went for the north. So it turns out the obvious region to look at is kind of near, it's kind of in the summer triangle. So near Cygnus, between Cygnus and Lyra is where we looked. And we were just trying to get a statistical idea of how many stars have planets and what kind of planets they are. And so it doesn't matter sort of where you look, as long as you look at a large enough sample of stars that you think you have a fair statistical sample. So that's basically what we did. And so you can see the Kepler field, in the summer, just go out and look between Vega and Deneb, and that's where Kepler was looking, and the field is actually pretty big.
Okay.
Well, the other thing about that statistical argument is that it's not gonna be the case in most cases that the planet is actually going to cross in front of the star as seen by the Earth. So you're going to miss most of them. And so you need to make a correction for the number that you see and then the number that you think you missed. So all the statistics that we give have been corrected for the fact that we know we would miss most planets, and we just get the ones that are in the orbital. We're in the orbital plane of.
So when the transits happen, how can we assume that the level of that brightness coming from that orbiting planet, or it may also come from any background ray of the cosmos? How we can assume that?
Yeah, well, this isn't a Kepler talk, so I'm not going to give you all the details. But the reason I was on the project is, people were worried, for example, the star varies in brightness by more than 1 part in 10,000 just due to sunspots and stuff like that. So the answer is that a planetary transit has a very particular signature. It has this kind of U-shaped signature. It's only going to last a few hours, and it's going to look the same every time the planet goes by, basically. Whereas other signatures will be different from time to time, like due to star spots. Actually, the most confusing thing was a background binary star that's an eclipsing binary would give you a signal that might look like this. So then we have to be careful about, well, are there any very nearby background stars, and how bright are they? And when we look at the Kepler signal, does it shift off the star when the transit happens and then come back to the star? There are a lot of checks, basically, to try to eliminate false positives.
So this particular pattern only happens when there's a transit.
Yeah, and of course, if it's a planet, it's going to repeat with a very strict periodicity. So that's another test. So we want to see at least three transits to know that the period is fixed.
Okay, thank you.
Yeah. Okay, so now let's talk about the concept of habitable zone, because everybody wants to know, is there life on these planets? And this concept is kind of squishy, and it's actually, astronomers don't really like it that much. But basically, when they talk about habitable zone, what they could mean is, if you took the Earth and you put it where this planet is, so at the same orbital distance from the star that we're talking about, would the Earth retain life? Then it's in the habitable zone. Or a more general use of the term habitable zone is, if I put a planet there and it had a reasonable atmosphere and it had water on the planet, could the planet have long-term liquid surface water? And the reason for that criterion is just that, the only life we know is Earth life, and it always seems to require water. And so this is just a guess, basically. So we don't know anything about life that's not Earth-like. This, whether it's habitable or not, doesn't mean that it actually has life on it. It just means basically it would have liquid surface water, or if you put the Earth there, it would still be okay. Okay, so if you actually want to know for an exoplanet, is there life there? The first thing you need to know is, what do I know about the planet's atmosphere? If it doesn't have an atmosphere, even if it's in the habitable zone, it's probably not habitable. If its atmosphere is too weird, it's probably not habitable, and so on. So we usually don't know that. I mean, basically, we hardly know anything about these exoplanet atmospheres so far. So when people say they found an Earth-sized planet in the habitable zone, you're like, okay, that's great. Guess we'll have to figure out what its atmosphere is, and so on. Now, the point about habitable zones and red dwarfs is because the red dwarfs are so much fainter, their habitable zones are going to be much smaller than for a sun-like star and much closer to the star, just because you want to get enough energy from the star so that the amount of energy reaching the planet is kind of like what we get from the sun. And if the star is 1,000 times fainter than the sun, you need to come, much closer to it to get that same amount of energy. So red dwarf habitable zones are very small and they're very close to the star. Whereas if you go to more massive stars, they expand out, and even more massive than the sun, it gets even bigger. However, that's kind of good in a way, and this is the basic reason why all these announcements of Earth-sized planets and habitable zones are around red dwarf stars. That's because the stars a lot, it's less massive, so that means the planet is going to pull it back and forth harder. So the radial velocity wobble is easier to find for a planet around a red dwarf star than it is around a solar-like star. Also, the star itself is smaller. So if I'm talking about a given size planet, it's going to block more of the light from a red dwarf than it would block from the sun, say. So they produce transits that are more easily detectable around red dwarfs than around solar-type stars. Then the habitable zone's a lot closer. So that means the orbital period is much shorter. So we're going to get a lot more transits or a lot more radial velocity wobbles. So they're easier to find that way. So all of those things add up to be that, especially for Earth-sized planets, they're kind of the only ones that we're kind of easily able to detect them, mostly as transits. And then you have to work really hard to see if you can get a radial velocity signature and get the mass of the planet. But we have masses for tens of exoplanets from that method. So here's just this is way out of date. There's way more Earth-sized planets around nearby red dwarf stars, but this just gives you an example. So a lot of them are close by, and at the time this slide was made, it was just discovered that there's an Earth mass planet around the very closest star to the sun, Proxima Centauri, which is a red dwarf. So they're common. That's
Red dwarf.
Sorry, I didn't hear the question. Okay.
I don't think there was a question. There was probably
Okay.
a background comment.
All right.
Sorry.
Okay, so we've talked a little bit about the basic idea behind a habitable zone, but as I said, you need to think about the atmosphere of the planet, and also stars many of them don't have a constant luminosity either. So that means the habitable zone is going to move over time. For the Earth, for example, obviously we're in the habitable zone right now, but the sun is slowly getting brighter. It's a bit of a mystery. So the sun was fainter in the past. So it's a bit of a mystery why the Earth wasn't totally frozen over for the first couple billion years. We know it wasn't from fossil records, but the sun was fainter, definitely. So there must have been a stronger greenhouse effect on the Earth at that time in order that the oceans stayed liquid then. So the greenhouse effect is another huge question for the habitable zone. What kind of atmosphere do I have and how much of a greenhouse effect does it have? Even today, the Earth would be frozen if we didn't have a significant greenhouse effect going right now. So although people worry about climate change, the truth is the Earth would be about 30 degrees centigrade colder if we had no greenhouse effect on the Earth. The main greenhouse effect for the Earth comes from water vapor in our atmosphere. And this CO2 that we're adding is, kind of a minor addition to that. But of course, obviously, it's important for humans. But the sun is getting brighter. So in about 500 million years, the Earth will no longer be in the habitable zone. The sun will boil the oceans in 500 million years from now. So that shows you that habitable zones move. But in order to assess the habitable zone around another planet, I need to know what the atmosphere is like that. How thick is it? How much greenhouse gases does it have in it, and so on. And we don't typically know that yet. So that means that whenever you hear people found a planet in the habitable zone, you can say, okay, well, that we should look at that planet harder. But we really don't even know if it's really in the habitable zone if we don't know what its greenhouse atmosphere is like. So people, calculate based on various assumptions where the habitable zones are, and it makes a big difference. Like Venus, for example, would be a much nicer planet if it didn't have a 90 bar CO2 atmosphere. That makes it extremely hot at the surface and totally uninhabitable. But if you took Venus and you put it where Mars is, and you didn't have such a thick atmosphere, it would be habitable. And you took Mars and put it where Venus is, it would have much lower surface temperatures than Venus does because it has a very thin atmosphere. So just to keep that in mind, a planet in the habitable zone might be a snowball planet, or it might be a roaster planet, depending on its atmospheric greenhouse effects, or it might be nice. Okay, so there are other issues with red dwarf stars, and this was the big one for a long time. Although, as I'll say in a minute, we don't think this is a huge problem anymore. But what is for sure is the habitable zones around red dwarf stars are so close to the star that the star will tidally lock the planet pretty quickly, in the same way that our moon has been tidally locked to the Earth. So that's why the moon keeps the same face towards the Earth all the time, and these planets would keep their same face towards their star all the time. The star just distorts the planet into a bit of an egg shape, and then the egg orients so that it's pointing at the star, and that's the end of that. So it's not that the planet isn't spinning, but its spin period is the same as its orbital period. So there will be if you stand here, the star is directly overhead, it'll stay there for the whole year of the planet. And on the other hand, if you're on this side of the planet, you will never see the star, ever. The sun will never rise. And so the planet's day is the same length as its year, and one side always sees the star and the other side never sees the star. And consequently, people thought, oh, that doesn't sound terribly habitable. In particular, what they were worried about is on the dark side here, there's never starlight. So doesn't it just get colder and colder and colder? And the water snows out, freezes out, and then CO2 freezes out as dry ice, and then maybe you get nitrogen freezing out, and basically you freeze out the atmosphere onto the backside of the planet. That would obviously be an uninhabitable situation. But as we've been studying climate change on the Earth, we've been running climate models for other planets, and it turns out that even if you have an Earth atmosphere on a tidally locked planet around a red dwarf star, you're going to get strong jet streams that carry heat from the day side to the night side, and that will be sufficient to not let the atmosphere freeze out. I mean, it will be cold on the dark side. We have Antarctica here on Earth. It sees the sun 6 months of the year, and it's pretty cold. Here, you never see the sun. So, yeah, it's gonna be worse than Antarctica, but not so bad that the atmosphere freezes out. So it's still habitable. You just need to be used to really cold environments, right? So here's actually a climate model for an Earth-like planet around a red dwarf star. You can see that the jet stream is keeping the equatorial part of the planet warmer, and then there's these colder spots here, and they're pretty cold. This is Kelvins, so room temperature is up here somewhere. So this colder than Antarctica, but it's feasible. And of course, the temperature on the day side just depends on where you put the planet. The closer you put it to the star, the hotter it is. The further you put it away from the planet, the colder it is. And you can adjust based on greenhouse effects. So you can get sort of any temperature you want if you fix the distance in the atmosphere correctly. All right, well, there are other issues with red dwarfs as well. One is that the red dwarfs are red. In fact, they're infrared, really. They should be called infrared dwarfs. So here's the visible or the electromagnetic spectrum. I assume this club is reasonably familiar with what that means. So between the two vertical lines here is visible light. This is where your eye operates. Here's the sun, and puts out most of its light there. And of course, our eyes have just evolved to use that fact. But for red dwarfs, the peak of the energy is out here, where you couldn't see it. This is infrared compared to the human eye. And most of the energy is out here, and rather little of the energy is in the visible part of the spectrum. So when you're asking yourself, what does the planet absorbing from the star, this is the spectrum you have to use, and it changes. The fact that it's like this, for example, snow is very reflective in visible light, as you all know, but it's not very reflective. It's actually rather absorptive out in the infrared here. So if I had a snow-covered planet around a red dwarf, it'll actually absorb more light from the star than it would have if it was around a sun-like star. So that's another factor. Then, then there's the question, is the planet totally covered with clouds? Clouds are very reflective, so it would get less energy to the surface as well. Or is it not cloudy, and in which case, is it water or land or what mix? Those all change the albedo of the planet and change the amount of energy that it absorbs from the star. So we don't know the answer to any of these questions for any of these planets yet. So that's another reason why you can't trust yet. People say they found a habitable planet. Yeah, maybe not. There's another issue, which is the main issue now, which is I study stellar magnetic activity, so this is kind of in my bailiwick. But presumably you all know that the sun is magnetically active. This is a picture of the sun in X-rays, and you can see the magnetic loops. This is the solar corona, not the corona that you see when you get a total solar eclipse. That's just that's visible light scattering off electrons. This is the real corona, which is a million or 2 degrees hot. So you need to use X-rays to even see it. But you can see that the plasma is really controlled by magnetic fields. You have all these loops. They're big. Here's the Earth scale. But the sun is a relatively inactive star. This is wimpy levels of magnetic activity you're looking at here. And you probably also know that sometimes these loops get twisted up by motions on the sun, and the magnetic field reconnects, in a sense, shorts out, and you get a flare, which is a tremendously powerful explosion, which sometimes blows off billions of tons of hydrogen off the sun altogether. These are called coronal mass ejections, and they can go out and hit planets, and they do. Including the Earth, right? So these are the aspects of magnetic activity that are of concern. One is that there's a lot of high energy radiation. This is X-rays. This picture is taken in ultraviolet, hard ultraviolet light, and then you have these high energy particles coming off as well. And indeed, the Earth is in the way, but we have our shields up. So, the Earth also has a magnetic field, and these particles from the sun are charged particles. When they encounter the Earth's magnetic field, they tend to go around it. So we basically have a big shield up, our own magnetosphere. A few of them get through, they come around the side and they reconnect in the magnetic field back here, and then they come back through the magnetotail and end up coming down at the poles. And of course, that's what the aurora is. Here's the auroral ring on the Earth. So some of the solar particles get to us, and they get stopped by our atmosphere, high up in the atmosphere. That's how the Earth is protected. But when you go to a red dwarf in the habitable zone, now you moved 100 times closer to the star in order to get enough energy from it. It turns out the magnetic activity on red dwarfs is often stronger than what we have on the sun now, and now you've moved way closer to it, and that's definitely an issue. So on young, even the sun actually, when it was very young, its flares were like 1,000 times more energetic than they are now, and its UV and X-rays were also hundreds of times greater. So the Earth actually was subjected to the very active sun early in its history. Obviously, we survived that. But if you went 100 times closer, would you survive that? That's the question. So red dwarfs can be quite a bit more active even than solar type stars. Some of them stay active for a very long time. That means billions of years, and they can have very large flares. So, for example, Proxima Centauri a couple of years ago popped off a flare that lasted, for a couple hours, in which the visible brightness of the star increased by 50 times, just due to this magnetic flare. As you can imagine, if you were on a planet and the star suddenly got 50 times brighter, that would not be good. Plus, there's this huge, the coronal mass ejections and generally a big blast of high energy protons whenever these things go off. And on the active red dwarfs, they go off every hour or two. So you're just constantly subjected to this stuff. On the other side of things, we said the planet was tidally locked. So half the planet never sees any of this. The star is not visible, and it's completely protected from anything the star throws at it. So, maybe that's actually an advantage for red dwarf planets. And in case you don't think this matters, it's mattered in our own solar system. So Mars actually lost most of its atmosphere due to this effect. It had a magnetic field early on, but it's a small planet. The core froze, it lost its magnetic field, and the sun just started hitting it with the solar wind and all these CMEs, and it is continually stripping atmosphere off of Mars. It's doing it today. We have the MAVEN spacecraft in orbit around Mars that actually measures the atmospheric loss from Mars due to the solar wind. Now, obviously, Mars is a smaller planet than the Earth, so it had more trouble holding on to its atmosphere anyway. But not having the shields up and having the sun blasting it made it much worse. And then there's Venus. Now, Venus, on the other hand, did not lose its atmosphere. I said its atmosphere is actually 90 times the pressure of ours at Venus's surface. So it didn't lose the atmosphere, but it's all CO2 on Venus. The basic difference between Venus and the Earth is Venus was closer enough to the sun that remember I said the oceans are going to boil on the Earth in 500 million years. They boiled on Venus, much earlier. And you boil the oceans, you have all the water vapor in the atmosphere. The sun is more active, it's got more UV. The UV is breaking the water up into hydrogen and oxygen. And then the solar wind is stripping the hydrogen because Venus also doesn't have a magnetic field. And so it lost all its hydrogen, so it can't have water anymore. The reason it has 90 times the atmospheric pressure is that because the Earth had oceans, the CO2 got absorbed in the oceans and turned into limestone and other kinds of carbonate rocks. So we have the same amount of carbon dioxide as Venus does. It's just all rock on the Earth, and it's all in the atmosphere on Venus. And then of course we're doing a little bit of a tweak with our fossil fuel burning to get a little bit of that CO2 back up into the atmosphere. At any rate, still not inhabitable, right? By our definition of we want liquid water on the surface. If the star strips all the water off the planet, that's no good either. So this is really where research is concentrating right now. Does this normally happen for all red dwarf planets, or are there ways to not have that happen? So there's basically two crucial questions. One, can the planetary atmosphere survive without a strong enough planetary magnetic field as a defensive shield? And of course, that depends partly on how massive the planet is. So it probably favors planets that are more massive than the Earth, can hold on to their atmospheres better. And then can water survive this early phase when the star is really active UV and X-ray and hasn't settled down to its quieter state yet? And that depends partly on how much water the planet starts with. So the problem is worse for red dwarf planets than it was for Venus, for example. The reason being that the red dwarfs, they're just slower. They do everything slower. They die a lot slower. So the lifetimes of red dwarf stars lie between 100 billion years and a couple trillion years, which means that no red dwarf that's ever been born has ever come close to dying so far. The universe is only 14 billion years old. So it's going to be another 10 ages of the universe before the first red dwarf dies. So they're slow. They burn fuel very efficiently and not much. as they're settling into their stable luminosity, they also take longer, and that's not good for this question. So the sun, drops very quickly down to its stable luminosity in like 10 million years, and the Earth doesn't even form until sort of maybe in here somewhere. But with red dwarfs, they take their time settling down to their stable luminosities, and so you'll get terrestrial planets forming while the star is still, several times brighter than it is going to be, which means that the planet is not in the habitable zone then, even though it will be later. And so the water will definitely be all water vapor here. The star is way too bright and hot at this time. And it's also the time when the star is the most magnetically active. And so that's the big question is, can water survive this era? Or are there ways to, sort of get the water later, maybe? Well, I said earlier, some planets are probably mini Neptunes and other ones are super Earths. And we kind of know where the dividing line is now. So if you plot, if you can get both the mass and the size of the planet, you can get its bulk density. And we've done that for, maybe 50 planets. And this is kind of what we've learned. If you had a rocky planet like the Earth and you add mass to it, it gets bigger, according to this sort of red dotted line here. That's what you expect. But at about 1.5 Earth radii, the observations show that the bulk densities of the planets suddenly start going down again. So these are planets that are bigger and bigger and bigger, but they're lower and lower density. So they're not rocky planets anymore. And we think the explanation for this is that you build up to a certain size of a rocky planet, and beyond that, it starts capturing hydrogen and helium from the protoplanetary disk. And it doesn't take much. You can have like 1% of the planet's mass be in hydrogen and helium, and you're going to get a big hydrogen atmosphere on the planet that we can't see through. So the transit method is going to say the planet's this big, but the mass of it is really given by this rocky core, but the density has been reduced by the fact that we think the planet's bigger than the bulk of it is. And those are the mini Neptunes. And so we do think that if you find and people still issue press announcements, oh, we found a habitable planet around a red dwarf or not around a red dwarf that's 2 Earth radii and it's in the habitable zone. Well, if it's 2 Earth radii, it's probably not. It's not a super Earth. It's a mini Neptune. And the thing about those is the atmosphere, even though it's only 1% the mass of the planet, the pressure at the bottom of this atmosphere where the rocky surface is would be thousands of times the Earth's pressure. And consequently, the temperature is thousands of degrees. And that's definitely not habitable. So these mini Neptunes, we don't think of as habitable planets. Okay. So fine. So if you go more than 1.5 Earth radii, forget it. On the other hand, we were just worrying about what the star is going to do to the planet, and it's going to strip all this hydrogen off. Well, maybe that's a good thing. Maybe you put a mini Neptune near a red dwarf and let the star have at it, and it takes off most of the hydrogen and leaves you with an Earth-like planet at the end. That's possible, right? And in fact, we actually see this process happening. We actually have observations. Obviously, this is an artist's impression, but you can take a spectrum of a system like this when the planet is not in front of the star and when it is in front of the star, and you can do it in the light of the hydrogen resonance line, and you can see that the transit of the planet looks way bigger if you look in the hydrogen line than if you look in light other than that. And we can tell that there's this giant cloud of hydrogen coming off the planet that blocks the hydrogen light from the star. So we know that stars do this. They strip hydrogen off of planets. And there's also, when you do the statistics of sort of mini Neptunes near stars, we find this so-called radius gap, where it looks like there's a bunch of mini Neptunes that are missing, and there's extra super Earths, and those are probably planets that have had their hydrogen stripped off. So that's one possibility. That this obviously would be pretty contingent. So most of the time it wouldn't work out exactly right, but it might work out right sometimes. But there are other ways that you can imagine red dwarf planets might end up with water. This one's easy, actually. If you form the planet with some hydrogen, some water basically in it, the star can strip what's in the atmosphere off, but there's a lot that's down inside the planet. In fact, there's a lot of water inside the Earth, and geologists are still puzzling about exactly how much it is. Is it another couple oceans worth or what? They haven't actually figured this out. But obviously, volcanism can bring water from the interior back to the surface, and you can just keep doing that. And after the star stops, stripping you, then you can start collecting the water. So and you got lots of time, right? So with red dwarfs, you basically, the stars are going to always be there, basically. The real limiting factor might be the planet might slowly freeze, and maybe this volcanism stops eventually. But if it's a 2 or 3 or 4 Earth mass planet, that's going to last a lot longer geologically active than the Earth is. So certainly there are instances in which this must work. Maybe it hasn't worked yet. Maybe maybe the universe isn't old enough for these planets to really get covered with oceans. But obviously, there's many intermediate states. Here's another way that's also obviously correct. You can store water on the dark side of the planet. We said, it's very cold there. Water's absolutely going to freeze out on the backside of the planet, and there are these winds, carrying the heat around all the time. So I can collect up a whole lot of water on the backside of the planet that's safe from the star. Now it's ice that never sees the star, and then later I can have volcanoes go off on the backside and release some of that water and so on. In fact, we think that the Earth went through a phase like this just before the Precambrian era. There's pretty good evidence that the Earth froze over for a while. Remember, I said we would be frozen if it weren't for the greenhouse effect. And so if things go the wrong way and the greenhouse effect gets a little bit too small, you can freeze the Earth without much trouble. Of course, we've had ice ages, so it's basically you just need the ice age to be a little worse. And then, but the Earth got back out of that snowball phase, and people are pretty sure that was due to volcanism that, sort of broke through the ice and put enough greenhouse gas back in the atmosphere to melt it. So that can happen on red dwarf planets too. So that, who knows? You should at this point get the feeling that, we don't know. These are all possibilities. There's lots of Earth-sized planets around red dwarfs, and we need to study them harder to assess all these issues. Okay, I'm going to stop here and see if there are questions about that part before doing the last piece of my talk.
Yeah, actually, there are a couple of questions that have come in the chat. There was 2 from Chris, and one was in reference to some chart you showed. And the question is, what was 25%, 50%, 75% BT in that last chart? So I'm not sure which chart.
That was the chart of albedo and and reflectivity with different emission curves on top of it. Yeah.
Oh yeah. Okay.
So what's the question?
What was the 25%? Yeah. What does that mean?
I think this is how much energy gets reflected, probably.
Are those like cloud cover? Are those the cloud cover lines? Speculating, but I wasn't sure if that was crazy or not.
Actually, this might be the land fraction on the planet.
Okay.
If you have clouds, it's quite reflective, basically, like Venus. So yeah, clouds would make a lot of reflectivity. I should say that, and I'll say a little bit more about this, but we do have some information about some exoplanet atmospheres they're not Earth-sized planets. We can only do it for bigger ones so far. And some of them have proven to be basically cloudy or hazy. In other words, we get a spectrum during transit and out of transit, and we see no spectral features in the spectrum. And people say, okay, that means there's some kind of large particles in the atmosphere that don't give you spectral features. So it's either hazes or clouds. And those planets are very hard to diagnose because it means that they have a high layer of hazes or clouds, and we're probably not going to learn what's in their atmospheres.
Mm-hmm. Then the second question from Chris was, do you assume planets are at the same orbit for their whole life? Don't planets in systems sometimes migrate in and out depending on orbital resonances and things?
Yeah, that's a good point. I had a slide about planetary migration. The talk's too long. I didn't put it back in, but yes, we know that planets migrate orbitally at least sometimes, and that's certainly another mechanism would be to have a water planet be further out, while the star is being unpleasant, and then have the planet brought in later. Most of the migrations, though, probably occur relatively early in the life of the system, say the first billion years or so. So that may or may not be very helpful. There's another way in which having extra planets could help, which is in a system that I'll talk about in a minute, the TRAPPIST system, for example. The planet's not going to stay tidally locked if there are other planets close enough to it, especially in orbital resonance with it. Even the moon actually, has a little libration. It doesn't completely keep the same face to us. It sort of wobbles slightly. You can get the planets to unlock if you have companions on either side of them that are close enough and at the right resonance to and so Mercury, for example, is a 3-to-2 spin orbit resonance. So it does have a day that's different than its year, but they have a ratio of 2-to-3. So the behavior of the sun in Mercury's sky is quite strange, and that's basically because Venus is near enough that it bugged Mercury. So yeah, there are definitely complications that can arise that could be helpful in some cases.
And then another question from Jin Seung is, regardless of global warming or climate change, sun will heat the earth and the ocean on earth is bound to disappear in the end. How can we consider the purpose of our current struggle or effort to prevent global warming or climate change?
Yeah, so my view of that is, the ocean's boiling is 500 million years from now. We totally shouldn't worry about that. Personally, I give the human race less than 10,000 more years to exist. So what happens in 500 million years is really irrelevant. Maybe I'm wrong, but it's far out enough that I think we don't need to think about it. What we do need to think about is what we're doing to the climate right now. And again, people say, "Oh, we're ruining the planet." No, we're not. The planet's fine. The planet's had worse greenhouse effects in the past. It will in the future. It's had all kinds of worse crises than this one. The problem isn't for the planet. The problem is for humans. Climate change is highly inconvenient. If we drown all our coastal cities, the planet could give a care, but the humans will. So that I really think, I do think climate change is a big problem, but I think it's a big problem for people. It's not a big problem astronomically speaking. But since we're doing it, we probably ought to stop.
Okay. One more question. Dr. Basri, you mentioned it's hard to measure exoplanets' atmosphere's chemical composition.
Yeah.
How about the planet's surface? Beyond the density data, what can we tell about the planet's surface chemical composition? Is there interest in knowing that?
Yeah, so there's a lot of I would say, preparatory work on that question. In order to get information about the planet's surface, we're going to need to separate light from the planet from light from the star. In other words, we have to image the planet directly. So the radial velocity method doesn't do that. The transit method doesn't do that either. We need interferometry that gives you enough angular resolution, interferometry and coronagraphs. So you need to block the starlight, and you need to be able to separate the planet from the star. There are a lot of technical schemes for doing this. None of them are in operation at the moment. They're very difficult, but we know how to do it, and I think it will happen in the next 10 or 20 years. And then once you can see the planet directly, you can watch, for example, if it's spinning on its axis, like if you watch the Earth, people have done a lot of studies about the Earth. For example, you can study the Earth using moonshine, Earthshine off the moon. That gives you the integrated, signature of the Earth. And yeah, whether oceans are facing you or land is facing you, it makes a difference. So we will get information about planetary surfaces when we can image them directly, and we're not quite there yet, except for the only planets we can image directly right now are sort of Jupiter-sized planets that are hundreds of AUs from their star. So that's interesting, but not for this question. All right, let me go on. It's fun to think about. I'm on mute.
Yeah, sorry, I was just saying that this was the last question so far, so
yeah,
you can continue. Yeah, thanks.
It's fun to think about what red dwarf planets might be like if they did have water on them. So the temperature question is one that the planet obviously has different temperatures depending on where you are on the planet. The subsolar point is the hottest, the backside's the coldest. Somewhere in between, it's in between. How much of a region that is and what it's like and so on is obviously depends on the planet. But actually, there was a recent paper where they studied the conditions at the terminator and showed that it could be nice there for some strip around there. And if it's not warm enough, you can move the planet a little closer. The thing is, you have planets at all distances from their stars, so you can always, and different masses and so on. So, and then the how much the atmosphere transmits to the backside. If the planet is an ocean planet, the ocean can move heat to the backside even more efficiently. And so yeah, we need to know more basically. But the terminator could be an interesting region on a planet. Or, if you move the planet further away from the star, maybe it's mostly frozen, but the substellar point isn't frozen. And again, if it's an ocean planet, you might have open ocean here and frozen ocean elsewhere. Hard to say. Also, there's been climate studies of red dwarf planets that show that the star-facing side of the planet, when the planet's sort of too hot, it tends to form a lot of clouds on that side, but that reflects the light away, so then it's nicer at the surface. So, it's right now we're just having a lot of fun with this. We don't know what any of these planets are actually like, but we can do studies of what they could be like, and that's basically what people are doing at the moment. Then, the dark side, this is more like the question, of is there life on Jupiter's moon, Europa? We know that Europa has an ice shell. It's a terribly uninhabitable zone. It's inside Jupiter's radiation belts. It's way too cold, et cetera, et cetera. But we know that it's got a protective ice shell of, tens of kilometers thick. And below that, there's a salty ocean, which is maybe a few tens of kilometers thick, and then under that there's a rocky body with volcanic activity, and so deep ocean vents exist on Europa like they did on the Earth, and people actually think life arose on the Earth at deep ocean volcanic vents. So the concept, as I said earlier, the concept of habitable zone doesn't really tell you about is there life there or not, and you could have life on red dwarf planets under an ice shell without any trouble. Then the stellar high energy radiation has no effect anyway, and frankly, what the atmosphere is doesn't seem to matter either for life under a thick ice shell like that. So, you know, that's all speculative, but, you know, it doesn't mean there isn't life on these planets. Of course, life like that would be very hard to detect. So, as I said earlier, the very closest star to the sun is a red dwarf, and it does have a planet whose lower mass limit is 1.3 Earth masses. So it's probably not more than about 2 Earth masses. So it's an Earth. It's an Earth, and it's in the habitable zone of Proxima Centauri. We don't know how big it is because it doesn't transit. So this is, you know, because it's around the nearest star, this is going to be one of the early targets for trying to image the planet itself. It's, you know, going to have the most angular separation from its star. Although, you know, because the habitable zone is so close to the star, it's still a hard problem. You know, here's the orbit of Mercury. Here's the planet around Proxen. It's right in there. But I think that within 10 to 15 years, we will have images of this planet. But, you know, so we don't know that much about it, basically. We just know it's there. We know that it's what its orbital period is, and its lower Earth mass is 1.3 Earth masses. Here's a better one around the red dwarf LHS 1140. So it's been detected by both the transit and the Doppler methods. So here's its transit, and here's its Doppler signal. And that tells us that it's 6.6 Earth masses. So, you know, if it's a transiting planet, you do know the orbital inclination. So then you get the actual mass, not the lower limit. So it's a 6.6 Earth mass planet. It has 1.4 Earth radii. So it's not into this mini Neptune regime, although it's about as big as a rocky planet can get, seems like. It's only 12.5 parsecs away. The orbital period is 25 days, basically. And so that's the day on the planet, too, because it's undoubtedly tidally locked. And it's in the habitable zone. If you didn't put an atmosphere on it, the temperature at the surface would be 235 Kelvin. And, you know, 270 is room temperature. And if you do put an atmosphere on it, it'll be warmer. So all that all looks good. You know, here, these are habitable zone boundaries here based on what you want to assume, and the planet's in the middle there. It's you know, its surface gravity is 3 times Earth, and it's a very dense planet. It's 6.6 Earth radii. I mean, masses, and 1.4 Earth radii means it's like denser than iron. You know, what are planets like that like? We really don't have any idea. But because it transits, it could be a target for the James Webb Telescope to try to measure its atmosphere using transit spectroscopy. So that's a real good candidate, not too far off. And then I'm sure you all know about this, but I just can't resist talking about it for a minute. The TRAPPIST-1 system. This is an amazing exoplanet system. There are seven known planets. They're all packed inside the size of Mercury's orbit. 3 of them are in the habitable zone. They're all kind of, you know, Earth-sized, or not too big, basically. The star is, you know, so here's to scale the star and the planets: Jupiter and its moons, and the sun and its planets. Not distance scaled wise, but size wise. So it's, you know, Jupiter and TRAPPIST-1 have, you know, sort of a fair amount in common. This is, you know, sort of 100 Jupiter masses, actually maybe like 120 Jupiter masses, and you know, so it's a more massive object, not a lot bigger though, and it has more massive planets, but not a lot bigger than these. This is definitely a target for James Webb. It's already been observing them. So the idea, let's see, did I put? Yes. The idea behind transit spectroscopy is that when the planet crosses in front of the star, some of the starlight actually goes through the planet's atmosphere and takes out a little bit of spectral signature. So if you measure very carefully the spectrum of the star when the planet's not in front of it, and then when the planet is in front of it, and difference them, you can see what the spectrum of the planet's atmosphere is. And especially in the infrared, which is where Webb works, there are water and carbon dioxide and various things will produce spectral features. And so this is one of the big tasks that Webb has. It does cosmology, tries to get the first galaxies, first stars, and so on. And the other thing that it does is it's trying to measure atmospheres on exoplanets using this technique here. So that's underway, and it's found some atmospheric constituents of some planets already, but we're very curious to see what it sees with the TRAPPIST-1 system. Okay, so that's kind of where we are right now. This is an artist's conception of the planet around Proxima Centauri, which would be this red dwarf here. You all probably know Proxima is actually a companion to the Alpha Centauri system, which is itself a binary star. One is very solar-like, the other one is a K dwarf. There may be planets around these as well, but there are at least 2 or 3 planets around this red dwarf. Well, we don't know what it's like yet. But it's a fascinating time in astronomy, and I think the progress that's going to be made in the next decade or 2 is going to be amazing. So thanks for listening.
That's great. Thank you so much for the talk. Any questions? You can unmute yourselves. I'm going to start with one question that came in. Actually, there are maybe 2 questions no, I already covered the one from Alan. Another question from Jensen. If human cannot reach habitable exoplanets live due to far distance, even the closest Proxima Centauri, what would be the purpose or meaning of our effort to discover them so desperately?
Well, this is a question that humans have always had, which is, are we alone? Is the Earth the only planet in the universe with life? That, to me, that's a ludicrous proposition, especially now that we know that planets are more common than stars, and many of them are Earth-sized, and many of them are in the right place. But this is science. So far we don't know any life other than life on the Earth. So that's the question, and we don't have to go there. As I've shown you, we have ways of studying this question without actually going to those planets. And people are working really hard on what would be the atmospheric spectral signatures that would tell us that there's life on a planet. And so, for example, the Earth has free oxygen in the atmosphere, and it also has free methane in the atmosphere, and those destroy each other. And the only reason that they are still both in the atmosphere is that biology keeps replenishing both of them. But then people try to come up with clever ways where inorganic processes could produce the same effect. And that's kind of where we are right now. Of course, SETI would be the other way. If we get artificial signals from some planet, that sort of cuts through all these questions in a hurry. So we're also pursuing that. But the answer is, this isn't about humanity going to other planets. This is about us understanding our context in the universe.
Okay. Let's see. You're getting a lot of compliments and a lot of thank yous in the chat here.
Thank you.
Any other questions? Feel free to unmute yourselves if that's what you prefer at this point. I apologize. I had to mute some of you during the talk because there was some background noise coming. But now is the time when you can unmute yourselves if you would like to do that.
Yeah, I'm reading the chat comments, so thank you all very much.
So I'm just curious, so since you mentioned that you are already retired, so how are you, I guess, what are different projects that you're currently working on after your official retirement?
Yeah, so because I was involved with the Kepler mission closely, I'm still analyzing Kepler data for what it tells us about stellar magnetic activity. So, you know, the main point of the mission was to find planetary transits. But in order to do that, we monitored, you know, 100,000 stars, actually close to 200,000 stars, every half hour continuously for 4 years. And we measured them, you know, to a precision that was, you know, better than a part in 10,000. Consequently, the stars left all kinds of other information in our data archives. So astroseismology is a whole field where you use the ringing of the star to understand its interior structure, like we use seismology on the Earth, and Kepler was good enough to produce astroseismic signals for many stars. So there's a whole bunch of people working on that. I'm working on the aspect of star spots. As I said, I was involved in the project because people were very worried that star spots would make it impossible to detect planetary transits. And early on, I said, no, that's not going to be a problem. The time scales on which the spots vary are sufficiently different than transit time scales that we'll be able to tell the difference. And that's true. But now we got a whole ton of information on star spots. So I am trying to extract the science from that. So I don't have to make any more observations. It's all in the data archives. I just can analyze it.
I see. Okay, gotcha. Okay. Well, I don't see any other questions here. So, and we are well past 9 p.m. So we should probably stop at this point. Thank you so much for coming, everyone, and participating. I'm going to stop streaming before we cut off. Good night.
All right. Well, thanks, everybody.
All right.
Say goodbye.